So it's my pleasure to welcome Dinesh Manocha, who is currently Phi Delta Theta Distinguished Professor of Computer Science at University of North Carolina, Chapel Hill. He has received lots of awards. I'm going to just mention a few. And these awards include Sloan Fellowship, NSF Career Award, ONR Young Investigator Award, and Hettelman Prize for Scholarly Achievements. He has written more than 300 papers. And some of his software systems actually use it, so I can say that we are users of his software systems. And along with us, there are more than 100,000 people worldwide who also use the software system. If I keep reading bio, I think you do not have time to give a talk. So stop here and let him go ahead and proceed with the slide.
Thank you, Satyendra. Good morning. Thank you for coming at 10 o'clock simple webinar. 10 o'clock talk, I have trouble getting up too, so I really appreciate it. It's really an honor to be here. This is a campus and a department and a lot of friends here. To see some good friends after a long time and lots of folks in engineering, computer science. So it's really an honor to be here and just seeing some very good stuff happening on robotics on this campus. So they give me a very exciting tour. And you've got a lot of cool stuff happening here. So I'm going to talk about some of the work we've been doing for a while. It's called motion planning, and it's kind of funny to say physical robots. It's kind of a very oxymoron title. Somebody said robot and physical, and I'll tell you why we use an oxymoron title to get some attention here. This is the work I'm doing. Most of my collaborators at UNC, some have graduated, but we have a good ongoing collaboration with folks at Willow Garage. I don't know how many of Willow Garage is a nice startup company in Palo Alto. We use a lot of results going on with them, and dealing with that. So let's talk about motion planning. And if any of you are taking a course in robotics, you probably learn about motion planning. So what is motion planning? And even though people don't trust Wikipedia, I got their definition. So it's what's called the navigation problem or the piano movers problem. And it's a term, even Wikipedia says, even Wikipedia is not good. It's a term used in robotics for the process of detailing a task into discrete motion. So robotics people have this vision, you have an autonomous robot who want to accomplish a task. Let's say going from here to here and get some coffee or cookies. How you take a high-level task description and the humans figured it out. I'm going to move my legs, move my arms away, navigate, do all kind of locomotion, do it. So this is what motion planning, this was the technology came up way back in the 60s. I know you got a lot of great AI people, and if you really go and dissect the words, let's just look at the term motion planning. What does it really mean? Planning, planning is a classic AI problem. I'm sure you have a lot of great AI researchers who know more about planning. And most planning you have a macro graph and wheel graph search. Motion, as what you learn in, let's say, a college class, is a continuous function from time to space. Something shown like this. And it turns out, so you combine the job of computing a motion using planning, you take the problem, continuous problem, turn into what is called a computational topology problem. You build some kind of a graph and apply planning like a search. That's a classic thing. So this is what motion planning is. Here's the definition if you take every course on robotics or in geometry. That you're given some robot and obstacles. People around your obstacles. We all humans, every time when we're walking, doing tasks, we are actually doing motion planning, implicit or explicit, whether you realize it or not. All animals are doing motion planning. So you're given that, and you basically given some kind of a description of the robot and the obstacle. You have to describe the scene. You got lots of constraints into the matter of a robot. We all have dynamic constraints. Some of you all talk about constraints, and we humans, somebody like me, at this age can't even run at 10 miles an hour, right? That's a constraint. Some of you can maybe run at 20 miles an hour, something like that. And this is called dynamic constraints, non-dynamic constraints. And ultimately, you compute a motion representation. But just look what humans are doing all the time. This is a grand challenge in robotics. Robots want to be as good as humans. Do it. Some of the earlier work, this is going back to the 60s and 70s, people do this problem in geometry. You're given some simple obstacles like this, a triangle shape, a rectangle, kind of a shape, and you want to move a ladder. So you take a ladder, but you rotate it, and you can kind of see, it's kind of, you kind of be a little bit smart if I rotate and do like this and compute this motion like this. A lot of name came from piano's mover problem. I don't know if any of you tried to move a piano. It's heavy. Okay, let's not worry about that. But even if it's not heavy, a piano is a funny shape. You know, it's just piano shape. They know the shape like piano. And how do you take a piano up the stairs like this? So this is actually also called a piano movers problem, ladder problem. People were dealing with this problem and said this is all motion planning. It's a classic problem. A lot of robots are actually, these are called rigid objects with 6 degrees of freedom, but we humans are actually a lot of animals, and all the cool robots you build are very complex articulated models with linkages and chains. So you have to not only just move the robot, but just like human, you've got lots of degrees of freedom. You don't realize it, but you use them all the time to go and grab a cup of coffee or just open a door. Even driving your car, you're all actually doing motion planning one way or the other. It's just part of life. Now, I give you the basic problem, but this problem is probably extensively studied for the last 30 years. I would imagine at least 1,000 papers. And there are lots of extensions of the basic problem. You have moving obstacles. In fact, even when you're driving, you're doing motion planning. You control the steering and the accelerator. You're looking for other cars, pedestrians, other obstacles. They're moving obstacles for you. You're saving. You're going through a mall. You are the robot. Everybody else is a bad guy or a good bad person, obstacle. You're navigating. So it's all motion planning. Folks who do assembly planning do that. There's something called non-norming constraints. Like when you drive a car, the common example I gave in my thing, why is parallel parking hard? And I'm sure you teach a control class here. If you don't think parallel parking is hard, put a trailer behind your car. Do parallel parking. If you want to be challenged, put 2 trailers. Why it becomes harder? Even if you have infinite space, this short parking space, but how do you navigate back and forth? Because your car, car has some non-norming constraints. Humans can turn like this, instantaneous, like a 0 radius turn. Car, depending on what speed you're driving at, if you're high speed, even to change a lane, you do longer duration because your radius is much bigger than that. So these are constraints, physical robot, physical device constraints, and you got to take that into account. A lot of I'll talk about here is uncertainty because, unfortunately, robots and the physical robots don't have a great view of the world. I'll come back to that. So this is well studied. And if you go back to the history, I give a little bit more computer science perspective, and I'm sure people in engineering take a different perspective. Perhaps the first work is about, let's say, 40 plus years old. I think that's the first reference. Nelson, the famous AI person, had the robot in Stanford, shaky, and they used something called visibility graph. It's a pretty common term in computational geometry and robotics. The field got a lot of mathematical formulation by a guy called Tomás Donald Perez, who actually also happens to be a grand advisor. He did this classic work in late 70s and early at MIT, and he used the notion of configuration space from topology and gave the whole field a computational framework. So this was his thing. This was it took on. So at least in the 80s, this problem was actually a lot of interest. A lot of computer science theoreticians jumped into it. It became algorithmically, how hard is motion planning? And it was basically a theoretical obsession, how hard it is. If you know computer science, NP completeness, P-space completeness, and there's some very famous names in computer science. You recognize Shaw, Sharif, Hopkroft, Wright, John Kenny, actually my advisor. He wrote a dissertation in 1987 called The Complexity of Robot Motion Planning, which got the best recent dissertation award. He showed this is the first most efficient algorithm, which is P-space compressing exponential. They were all the theoretical results, but they were all showing actually all results were negative. The problem is too hard. That yes, it's important, but even a simplest problem takes exponential complexity of number of degrees of freedom. A rigid object has 6 degrees of freedom. A human has 100 degrees of freedom. It's too hard. So theoreticians said, okay, we show the complexity. They moved on. It was there. A lot of excitement came actually in the 90s. So we knew theoretically the problem is too hard. We can't design complete efficient algorithm, but people said planning across all over the world. So in the 90s, there was a lot of trend towards designing practical algorithms. A lot of work done by Jean-Claude Letron and his group at Stanford, Lamont in France, India. They started developing what in computer science called practical randomized methods. You take a lot of random samples and combine them, and this was actually a very pleasant change. Here are people spending all this very heavyweight math, showing the completeness result and showing very negative results, and you come with a simple and dumb approach, like the basic planning algorithm sample base can be described in 2 pages, and you do it, loss collision checking, and they start implementing. Even though they're not theoretically complete, they seem to work well. So it was wow, from theoretical hardness to practical things was a good thing. So people started saying, well, hey, we can make planning work. We learn computing getting cheap, we can do that. So people started saying, even though it was theoretically a negative thing, it started becoming a technologically a success. So the last 15, 20 years, here are at least 9 big applications where people have used planning to get very impressive things. Randomized planning. And I'll show you a few of them. But this is, you could give a whole talk how planning has been applied to get a lot of success stories. So some of the places that I'm aware of and do it. So we have done some work with this too. Like these are folks like General Electric. They make CAD parts. And for example, you design you open up a car. Can you remove a part, without, there's enough gap between that? So before you go and build a physical prototype, they build a CAD model, and there's the thin wiring, and they let you know whether this part can be removed like this. Automatic planning, like that. A lot of this, this is car engine design. How do you place objects? This is seats, suspension, another kind of thing. They use planning for this routinely all the time. Assembly planning. A lot of the assembly planning. You always, whenever I get one of these assembly of furniture, I can never understand those 2D layouts. You try to break 10 things. I'm not an engineer like you guys are, but really, how you bring parts together, it's all actually a planning problem. Put this on top, put a screw, put like this. These are all planning problems, and you can actually turn them into quite effectively. There's a lot of work that actually, believe it or not, in cable harnessing. If you ever talk to Boeing people, one of the things that they deal with when they design the new 787, which is a huge nightmare, they've got tons and tons and tons and tons of cables. How do you even if you ever open up airplane, open up the floor, you'll be amazing how many cables you find. It's incredible. How do you do this? How do you do 3D pipe design? I don't know if any of you do like a power plant. You've got amazing amount of piping. How do you do the layout of pipe? You can turn all this into a planning problem. Just for that, some of us come from computer graphics. We all watch these cute-looking Pixar movies, Toy Story, animated characters. They also use planning. How do you plan character motion? Your animators sit down and come with all the automatic character motion. Planning. Getting more serious, surgical planning. So when you do, for example, something like cancer treatment, you got a radioactive machinery here. You need to make sure that you only deliver this radioactive dose to the place where cancer is, and not anywhere else, because you can't damage the organ. So they can do planning to exactly precisely position this tip, and make sure you get the right amount of dose at that place here. This again planning the location and orientation of that. And I'm sure a lot of you folks here, Amitabh, other people do a lot of computational biology research, folks have been doing prediction of molecular motion with confirmation search. There's been a whole amount of research on wave planning. And the last but not the biggest success story that got a lot of press attention was in autonomous vehicles. DARPA had the grand challenge for many last decade, and way back in 2005, where Stanford came #1, they were designing an autonomous vehicle. You given a vehicle with all kind of sensing, LiDARs, cameras, and they came up with a planning for a 100 km/mile dial path. And more recently, you've been hearing, Google has an amazing group. They're driving all over Bay Area with Prius, autonomous cars, and it's all planning. You basically sense the environment, look at everything. As I told you, driving is a planning problem. You drive back tonight, think of motion planning, but focus on driving, So that's what it's all about. And we ourselves, also did a thought about planning. Some of the work that UNC did over the years was, we found out, so all these randomized planners actually spend a lot of time on collision checking. They have objects, they take samples, and they just want to know the answer. This is object and this object colliding. It's a very classic geometric problem. If they're not colliding, how far apart they are. So surprisingly, in all these planners, 90% of the time is spent in collision checking. So if you want to make planner fast, that's a lot of time goes. So this is where a lot of software we put together comes up. And some of the planning problems are easy, some of them are hard. And you can relate to it, You can perhaps walk out of this door. It's not very hard. It's kind of open space. Planning is easy. What if we deal with a tight space? The term they use in planning is called narrow passages. Because planning is a high-dimensional problem. We humans are good at navigating in three-dimensional XYZ space. But somebody like me still has trouble dealing with a high-dimensional rotational spaces. Let me give you an example of what it comes out to be. I don't know how many of you have seen this alpha puzzle. I don't have a physical version of that. It was a benchmark that you got to take this up. And even robotics community took them, like in the late 2000, took them a lot of research to separate the alpha puzzle, it looks something like this. So you can probably appreciate, you could really figure out, you rotate alpha and do like this, a very tight gap right there. It's hard to appreciate without a full actual prototype. But this was actually, a lot of humans, if you give it to them, I can give you a test. How long do you take to separate the two? Some smart person will do half a minute, 1 minute. Some could not even do for 20 minutes. They've done this test like this. It's a planning problem. This is some work we have to do with folks at Renault through a company called Kino. So when they go and assemble the car, they actually put the car seat first, and then they seal the roof, and then they put the door. If you ever go and ask, open your door, that's you're going to replace your car seat. Now you don't do this very often. Would you take your car seat out of the driver's side door? Go and try it, if you assuming. It actually turns out to be, so they used to make physical prototype, Renault. And which costs lots of money, takes weeks. And we told them, no, you could do it. But you'll see, this kind of planning is hard because you've got a narrow passage. So this is like, it's got a very tight space. You got to really move. Even humans, if I'm walking in a very tight area, slow down and walk very carefully. So really you have to do pretty nasty manipulation with the car seat to really get this out. It's called planning in a very tight space, and how do you deal with that? So this is kind of thing CAD people do it all the time and do it. Some other work actually we did is also folks with in medical applications. So this is the folks we got folks with Johns Hopkins. They do this like liver cancer treatment. They put a catheter to your artery here, and it has to go to the liver, and then deliver the drug. The challenge in design is how to design the catheter. If the catheter is too thick, it can drop to your artery. And if it's too thin, you can't deliver enough drug to the kidney. It's called chemobolization. So they've got a model of artery, it's reasonably accurate, but this is what is called deformable robot. Robot could deform like a wire, like this. And how do you figure the right radius, which won't damage the artery, but still deliver the drug to the thing? So you can see we did a finite element simulation of this catheter. All planning was done, and you basically kind of going through it. And how you perform this turn, this is called deformable robot. This is the work we did about 5 years ago, combining a lot of physics-based simulation, a lot of work that Ming does at UNC, and then combining that and kind of going to the liver. And you can now see, could I increase the diameter of my catheter without rupturing the arteries? So this is the kind of problem, believe it or not, come across all the time, but it will come up. And this eventually, the artery is a pretty nasty thing, and they actually have to go there, and you actually see this is where the cancer is, and now, you go and deliver the drug there. This is how they actually do a lot of liver cancer treatments like that. It's not just saying now this is all which is their application. One of the places I think we've been doing a lot of recent work is actually gaming. Gamers want to have characters, and they want to have autonomous characters and do it. Actually, we've done a couple of licensing of technology gamer recently. So this is some technology put together with IKEA, and you can see this is the typical gaming. Gaming is not fun without good graphics and good music. Multi-robot planning, they're all agents. They will go and collect the rocks, and they do the task. They move each other without collisions. It's like how humans would do. And if you're playing this game, you can do this thing. And there are a couple of more little games. I can tell you which we're using this planning stuff. So, great. There's a theoretically hard problem. A lot of practical methods came up, and we have all these great success stories in 10 different fields. Is it a solved problem? So the question motion planning committee asked after 40 years of research is a mission accomplished. So Jean-Paul Lemond is one of the leading researchers at CNSRS in Toulouse, said planning is a technological success. He gave this keynote talk at Robotics conference last year, but outside robotics. So the problem came up from robotics. It has been a great success outside robotics, but what about the robotics part? And planning still has not been useful for, now we go back to physical robot. Robot is an oxymoron term. A robot is a physical device. The planning was supposed to do for this robot, but it is everything for CAD/CAM, game, biological molecules, medical simulation, but not for this. But when it comes to physical robot, if you look at most robots, they do very, very simple and dumb planning. Even you look at iRobot, you have a vacuum cleaner, it's supposed to figure it out. You know what kind of planning it does? It's actually very dumb planning. Not all the machinery that I showed you here. They can't do it. There are reasons for it. You're looking at robot, even at cars. Cars are very constrained thing because you're basically sensing the environment. You get a road map. And highway, luckily, if you're a good driver, you stay to your lane. It's a very constrained problem, and you can use it. But general planning is still too hard. So now people are looking into why motion planning, which was actually a problem designed in robotics, has not been used for physical robots. What prevents us? And now comes all the challenges. So a lot of time, if you think of how humans operate, and a lot of robotics is driven by human behavior, humans have this loop of we sense the environment, we plan, we do the motion. You're implicitly doing this sensing, planning, motion is a loop going on in real time, all the time. Now, typically, this kind of task execution is real-time feedback, and also dealing with the uncertain world. You don't get precise sensing right there. And how do you take an arbitrary task to a sequence of motion planning problem that big take with perception? And to be honest with you, this is a part of research you don't understand. How does human perception sense the environment, take a planning? It's not typical AI graph search. We don't know what our brain does. Come with the motion. And robots will do the same way. We don't know how to do it. This is one of the best examples. All the research I showed you in CAD/CAM, games or thing, this is what we do in computer graphics. We generate beautiful 3D models, precise 3D models. We just take it for granted. And then we have a precise 3D model like this. We can do our planning. Hey, I can do random sampling, I can do collision checking, I can do very fancy physics, I can do it. But today robots, they have sensors. And I'll show you more about the sensor. They have think of this way, most humans have corrected 20/20 vision, but they got on 20/80 vision. It's something when a child is born, they're not 20/20, they develop over the period of time. If you're 20/60 or 20/80 vision, would you be driving? Think of that way. So that's an analogy, I know about robot, but this is the kind of sensing robot they get a very imprecise version of the world, autonomous robot. And it's almost like you're driving with a 20/80 or 20/60 vision, and you can imagine your classroom. So this is where a lot of challenge comes up. And so what we are going to talk about, what we've been doing recently is, there are a lot of people now working on, let's make motion planning. The original goal of the problem was in physical robots. Let's come back and do it right. We kind of got diverted into CAD/CAM, gaming, biological applications, medical simulation. And they're good success stories, don't take me wrong. They're great success stories. But let's come back to the original problem. Can we do for physical robots? In fact, I'm doing a big workshop at ICRA on this thing, but I'm going to just tell you about some of the work we're doing at UNC and what we're doing is. So the first one we're talking about collision checking, as I told you, all these planners spend 90% of their time on collision checking. And this is a problem lots of people have worked on for at least 30 years. But now they live with noisy point cloud data. Let me start with this. So most robots, I've been now working with folks at Below Garage, they have two kind of sensors, there are a lot of cameras. And we all know cameras are becoming cheap, Your iPad comes with 2 cameras, your iPhone will have a bunch of cameras. Cameras are cheap. Not only they have cameras, but they also have laser scanners. Sensing is becoming cheap. You can put a laser scanner here, all over the place, you are computing. Sensing is cheap. But literally, when they perceive the world, as I said, they don't see something like this. They give you more like what I call a 20/60 or 20/80 vision. And in fact, what they give you, even with stereo cameras or LiDAR sensor, they give you a point sample of the world. You're getting this kind of point sample at 30 frames a second, or even 60 hertz. You got sample. Now, how do you do your navigation or something? Imagine you go to grab a bottle of water or a cup of coffee, something like that. If you had 20/80 vision, you get a very blurred vision. But you were to grab a cup and still hold it stable and drink hot coffee. This is the kind of thing, you almost think of an analogy like this. And of course, the biggest thing which is happening recently now is, thanks to Microsoft Connect thing, people are suddenly getting indoor sensing, 3D point cloud. It's just going to get better. Because this is giving you a big push. It'll make $150 you can buy this RGBD camera. It's going to get better, and people are doing all cool stuff. It's going to happen. But the current Connect even give you something like this. This is a kind of a point cloud. You can together like this. Some results get from some books at University of Washington, a group at MIT, and this thing. So all the work I showed you planning success story was based on wonderful exact geometric representation because they were virtual objects. But this is real world object. You're given this thing. How did you planning, navigation, and grasping, and scene reasoning? Implicitly, you're reasoning about the space. And second thing is you're getting this data at 50 or 30 to 50 frames a second. So you got a less than 20 millisecond budget. You got to process the space. Human brain is doing it. So let's look at this problem a little bit more from a computer science view. If you're given like a nice simple 2D shape on the left, if we zoom in computer graphics in robot motion planning, what you get is some kind of a sampling of this. So there are two kind of errors for discretization error. You don't know how to error sample it because if something got occluded, you got pretty bad sample with this. And then secondly, each of your point is inaccurate. There's some sensor error. You do vision algorithm, that error in there, connect the depth error in there, connect is really optimized for that distance. If your room has good lighting, something like that. So you got position error. So now you're dealing with a very noisy world description, the real world, how you do it. So I've been doing collision research for almost 20 years now at UNC and ask the question on the left, hey, we all know if I give you two objects, red and blue, do you collide? You said, duh, of course they do. And we get done a lot of algorithms to do it right. But if I give you 2-point cloud like this, no 2 points are matching. Okay? Do they collide? What do you say? So as I said, now you're living in a world with a 2080 vision, with a very precise world, but that's what the robot has to do. Do it right. Now, how can we do it right? So there's two ways. There's a lot of work for both computer graphics and other things. There's a whole area in computer graphics called point-based graphics. In fact, Amitabh and his student done some very nice work on point-based rendering, point primitive. So one possibility is you take the point cloud. There's a huge literature in computational topology, computational geometry. You try to reconstruct a continuous representation, and then go back and apply your classic continuous representation thing. Hey, we know how to do this. And we know how to do this, so what's the big deal? And we do this. Well, it turns out, actually, this reconstruction process itself is quite noisy. If your data is noisy, okay, if you have all the sensing error, discretization error, you can't really bound them. All the beautiful computational topology algorithms assume some point cloud sampling, do it, they don't do it. So actually, if you do this, the two problem comes up. In fact, I would say reconstruction is more difficult than collision checking. So my goal was in collision checking, but the process, I introduce a more difficult problem. It's noisy, it's slow. Even a good reconstruction algorithm, we given 10,000 points, will take 5 or 10 seconds. And I'm looking for a solution to take 20 milliseconds. So what do I do? Okay? So reconstruction process is not robust, very sensitive to noise and high order features. If I get some bad reconstruction, don't get a sampling this sharp edge, you will never get reconstruction. And it's slow, and ultimately we want yes, no answer, but it will be very sensitive to noise. So basically the answers that you'll get will probably be meaningless. So what do we deal with? So we come back after doing a lot of our life spending in exact collision checking for about 15 years. We said, now how do we deal with collision checking on noisy point cloud data? Because remember, this is not exact data, so don't expect an exact answer. So we start looking at probabilistic collision detection. What is the chances of maximum the probability of success? It's like a very statistical measure. It's pointless to even think of an exact answer on a noisy data like that. So this is a classic result we know in computational geometry. We always tell our people that two objects don't collide if you can find some kind of a separating surface. This is a classic geometric formulation we use all collision for. And can we exploit this somehow? So we go back to the noisy point clouds and say, can we find a separating surface that separates the point cloud as much as possible? So this is the intuition, as much as possible. We'll turn this into some probabilistic measure. How do we do it? Now, this is some very nice work done by student Japan, and he actually brought machine learning ideas to this to see what we can do it. And again, you can actually turn out that you can, if you're given an exact point cloud, if you don't have position error, you can turn the optimizing the separation error problem to what's called SVM, support vector machine. If you know machine learning is a very common term there, algorithm. And then also you can apply supervised machine learning methods for geometric classification. Because you're doing classification of data. Are these point clouds overlapping or not overlapping? You can do this. But even those techniques don't work well because they are really designed for exact point cloud. So if there was no position error or a discretization error, we could do that. But you have now each training point has this thing. So how can we do a machine learning terminology with robust classification? So it's kind of a kind of machine learning problem. And again, if you know machine learning, this is all trivial stuff to start, but you know, this is standard singular support vector machine, you find separating surface. But now when you got robust classification, noisy, how do you do it? You start with a Gaussian distribution assumption. I've been trying to figure out, everybody's not generating connect data, you got connect in your lab. Do you know what kind of noise you get? Is it Gaussian or not? I'm trying to figure out what answer to that yet. And you know some measure. Let me know. I'll let you figure out the probability distribution. I'll ask you to do the hard work and do it. But ultimately, what we do is we come up with some classification metric of collision probability that we associate a probability. Is the separating surface all the points on one side or not? And ultimately, we're trying to do robust classification in a statistical sense. Let's reduce it to. So I won't bug you with all the details, but if for each point you basically cluster them and keep only one cluster, you find the collision probability. And the object, which is defined by one probability, you put them together, you get a notion object probability. Now, there are different ways to combine this metric, and we're playing with different metrics. How do we do it? Just to show you an example of this, this is how we teach it. Now, on the left-hand side, these objects are really penetrating. We call it deep collision. So in this case, we get collision probability near 1. This is an easy case. Objects are really penetrating in the collision. The very right-hand side, the objects are well separated. This is also easy case. In both collision terms, these are called the easy case. Typically, the hierarchy do it very well, easy collision. The challenge comes in the middle where the objects are just touching. And this is where the noise will hit you. But you remember what task you do? When I want to grab this bottle, my hand will be just touching. I don't really penetrate. I mean, the bottle can deform, but that's where all the interesting stuff happens. So this is where probability comes in. What do you want to classify this scenario? So the best we claim is this probability is 0.5 because a very small perturbation in noise data will change the outcome. So this is how we classify probabilistic collision detection, and this is the hard case. You bring the probability half, and this is what it is. And you change your navigation planning scheme to take this into account. That you're looking for a case where collision probability close to half. That's a context scenario you want to go into that. And this is how we're describing mechanical planning. So we did a lot of work on this. This is we do some, we just did some simulation. And simulation, we took some point cloud. We actually also did some exact triangle mesh. That's shown in blue. So there are two objects. They're first basically, collision probability, they're not colliding. And then they go just collide, they penetrate. This is the exact answer right there. But then you take the point cloud. This is right here, the separation distance. Right here it goes up. Probabilistic collision detection, our algorithm. So basically, we try to look at separation distance and show that the regression curve that we get from our probabilistic collision algorithm actually match the separating distance. So you get a bunch of answers that the two curves match, and we believe statistically speaking, this is what we wanted. This is the feature you wanted. And if you do something like this, we say, okay, now something like this is where the distance is a deep collision penetrating, have called easy case. This is the large distance configuration, and this is the where in contact configuration. So this is where our probabilistic collision detection can give you an answer sometime between 0.2 and 0.8, which means you're close to where the toughness is happening. So this is how we can do robust classification of collisions now, and life becomes easy. We did the same simulation with large noise, and again, of course, there's more deviation error, but again, our regression curve came close to matching this. So this gave us a lot of hope that at least we can do this well and we're getting good match with it. This is of course all simulated data. How good is it in practice? So we went and worked with the folks at Below Garage, and this is, let me just show you an example of how the Below Garage sensor works. Sorry, I pressed that wrong. This shows you a Below Garage sensor. The video will demonstrate what's going on there and how they get the sensor data. And we put our stuff into ROS, it's the into integration. They use the thing. So they have This sheet demonstration of they call the LiDAR sensors. And this is how you're actually getting it. This is the data they're seeing on the fly, point cloud data. This is a gripper. And this is how they want to go and grab, but this is exactly the data that you basically draw for visualization, what a below garage sensor is getting. And they put all these demos like this, you got to go and grab this tape or get this Coke bottle, get these demos like this, controlling with this thing. So we're trying to see, whether we can get robust classification. So our initial results are quite promising. We still do a lot more testing. So I can't say for sure this is the way to do it. Give me another 6 months or 12 months to do it. But we are finding out that we're doing a pretty robust classification of collisions with this point cloud data. So at least with below garage we do it, and in fact, somebody recently approached us because now people doing connect for everything. The people, Microsoft believes that connect will be the user interface of the future. Like all your set-top boxes are going to come with connect. There will be no remote, you're doing all this stuff. And something I want to go and track the data. So we're also looking at some connect data right now if you can do the probabilistic distribution. But again, this is the real world, but robot world is this is a 2020 vision and that's a 2080 vision. And you classify, see you go and grab this bear can, you go and just grab it right there. So you need a robust classification to get this right. This is what we're dealing with. So we got the actual data here, and again we did the same plot. So this is the solution of our algorithm. This is a reconstruction, which is actually noisy data. This is kind of meaningless. We just did a reconstruction assuming the data was the ground truth, but it's really not the case. And again, deep collision, large distance, and in contact configuration like this. And again, we saw a good kind of math to this.
So what is the deep collision in this context?
So deep collision in this case was, basically in the simulation, these objects were really penetrating. But that's, for us, collision sand is an easy case. There's so much deep penetration that noise is not so sensitive.
Something physically how
physically it doesn't. Physically it doesn't. So we basically did the, this was just the point cloud. Then we took the data.
Right.
All the data was doing was actually capture the statistical noise from below data. But in our simulation, the first part was done by our simulator that we really move the object inside a gripper and just see how the classification was happening. Right there. So again, these are initial results, quite promising, but we are doing more. And ultimately, this is point cloud classification, a very different kind of collision checking. But we are right now 1500 milliseconds. The code is optimized. We can do incrementals, SVM. We can do hierarchy, the optimization we can do. We can begin on 10 millisecond budget, but not this thing. And the main thing is, that really, if you think about in-contact configurations, strictly speaking, correspond to non-zero measure in C space. But if a mesh-based collision checker, is fundamentally not the right solution. Because you basically do a class zero measure set, and it's just not the right answer, and that's what it is. So this is basically so much on that front. So this is to how do we noisy data. The second work that we're doing right now, is trying to build out use of GPUs to robotics. And again, there's a lot of work happening here. I know Amitabh did a lot of work on GPU for information thing. Ramani is doing a lot of GPU work for acoustic. Satyendra student, a lot of people doing GPU, and a lot of people we have done. So Below Garage has this manipulator they sell you. The market price is $400,000. If you're a good academic friend, they'll give you 30% discount. In a nice support letter and put a press release if you buy it. So this is a notion of a mobile manipulator. They're selling this thing. If you just look at the hardware, so this basic version has 2 quad-core Xeon processors, Intel, which have 8 cores, and a lot of memory. If you're a more powerful robot, they can put 16 cores or 32 cores. But this is a mobile platform. Okay, guess what's the 2 biggest challenges? It's the power. So they go and charge this robot, do some tasks, and this 1.3 kilowatt hour, we all talk about laptop batteries, we dealt with. Imagine if your laptop has 2 Xeon quad-core processors, I'm sure, Ramani, you need that for your acoustic simulation. Like we're talking like how many cores you need, but will that battery last across the coast, traffic? But that's what it is. So yes, you can hardware takes cost, but really who's going to, these are mobile manipulators, How are you going to drive it? So, and of course, as I told you before, any planner has this loop implicitly doing your sensing, planning, moving. That's a basic loop that, this is what happens. Let's assume your sensing is good, we're getting sensing achieved. Yes, you can classify sensors very well, but you still got to plan. So you need real-time planning. So most of the work I showed you of success story robotics before, most of them are actually offline plans. It's okay, I build a virtual prototype, you take 20 minutes, you tell me I can remove the part. Surgical planning takes 2 minutes, but just get it right. You know, and most of the planning were game a little bit more, but did a lot of planning. So the question is, you know, robots deal with this thing. So one thing we start looking at can do real-time planning. Something people have not addressed before for these kind of robots. So what we started looking was, okay, you know, we have a big, we have a lot of core computing power, but that's what Willow is doing. They think there's a lot of computing power to process the sensor data and the planning, but then they're saying that they're not good enough. And in fact, I've been working with them to convince them to use the GPU, and somehow people outside graphics have this fear of GPUs. You know, what's GPU, what is CUDA, is it open source, what if NVIDIA goes out of business? There are all these questions, you know, how to make it work, and we can talk about that later on. So some of you probably know about GPUs. If you don't, you know, GPUs is your every computer computer, pretty much every desktop or like client computer comes with a GPU, graphics processing unit, which is like we think of the many core programming processor. It has high number of independent cores, so you have a low and a high end. A lot of simplification, vector processing on that, but it has a very what I call unique memory processor. You know, it has its own memory model. You've got a lot of cores, you think of multiple processors, but the synchronization them is between very limited. You can't do the classic parallel programming very easily. It's only by a main memory, and there's no memory consistency model. Why do we GPU? We have been showing this chart for the last 10 years. My friends in NVIDIA love it, my friends at Intel hate it, this living thing. That what you see here is to show, if you look at the Moore's law curve from like 2003 to 2008, you know, the new Moore's law is computers don't get faster, they get wider, the number of cores. That doesn't mean your software runs faster, it's very challenging to get parallel programming. But at the same time, the so-called peak performance, which to be honest with you is a meaningless marketing number, but peak performance of GPU touching teraflop. And I tell them, if you can even exploit 5% of this peak performance, or 10%, for $500, you're still beating the best CPU. So if you get 20%, 30%, 40%, so that's what it comes down to. Can we design a good GPU algorithm application? There's a lot of folks right here. That's what it is. Of course, GPUs have been doing a lot of work. You know, there's a lot of work. Lots of people have done, so I'm not going to worry about that. Some of the earlier work we did, we were one of the first few GPU motion planning papers we published in 1999. We show Warner diagram, and the application we're doing was motion planning, but that was low degree of freedom planning. You reduce the problem to a 3D Warner space or 2D, and do real-time Warner computation planning. That doesn't extend to high dimension. It was very challenging, so we couldn't do it. For high dimensional, I told you, people use what's called probabilistic planning, which has been success story behind all this stuff. But how can we make probabilistic planning this thing? So this is some of the things we've done in the last couple of years. First, real-time, at least 10 to be real-time GPU-based high-dimensional planner. We call it G-planner. In some ways, parallel-friendly, but how do you exploit it? How do you make it parallel-friendly and extend? Also, how do you deal with uncertainty? Uncertainty, dealing, sensing, and all that kind of stuff. So just in case you don't know about planning, like a short overview, you're given this space, and you're given obstacles. Of course, you don't have explicit representation of those areas. So the obstacles are the region that you want to avoid, but you want to plan a path which lies purely in the yellow region. So what they do is they take a lot of samples, random samples, and do collision checking, and based on collision checking they figure out whether this point shown in pink or the purple is in the yellow region or the black region. You classify. This is where the collision checking happens. You take all the points in the yellow region, you join nearby points, you turn to a combinatorial search problem. And if you can find a path to this graph in the yellow region, free space, find a path. You can put kinematic constraint, dynamic constraint, harmonic, that's how this whole process works. And this is basically connecting to it. So what we did was, we looked at the GPU planning framework, and this is how a planner kind of framework, what's called probabilistic roadmap planner works. This is this pipeline. You generate samples, compute milestone, perform proximity, local planning, query, and search. There are like lots of papers, but it's a broad framework they follow. How do you do the right sampling? There are lots of papers on that. How do you proximity computation fast? There's a lot of collision checking happen. How do you local planning? Query connection. So there are a lot of algorithms feature this step, but this is how they do it. We look at this framework, and we said, okay, let's look at what's a common module that takes all the time, because we wanted to run the entire planner on GPU. A lot of when people do GPU-based solution, they take one module, the intensive module, put that on GPU, CPU controls it. But what happens in that case is, a lot of data goes back between CPU and GPU, synchronization, data transfer, that becomes a bottleneck. You don't get big speed up. So our goal was to get the speed for the entire planner on the GPU and deal with it. So this is the planner stuff we have here. Construction come up. I won't go into details of that, but this takes lots of stuff, and we look at the two big bottlenecks are very high number of collision queries. Even for simplest planner, doing million collision queries is not a big deal. You do a lot of random sampling. If you can narrow passages, even more sampling. That's how probabilistic planners work. And there's one more problem, which is versus the database literature called nearest neighbor search. You're doing high dimension. You figure out what are nearby samples to you, you join them, you kind of locally build a global roadmap. This is how you do plan, this is how it really comes out of there. So again, I don't want to delay or bore you with all the details of that, but for each step, you have to make sure every step has to work on GPU. Parallelization was key. We did that. Again, parallel sampling, a lot of collision work we done in the past, hierarchies. I'm going to go this quickly. You do this fast. Bounding volume hierarchies, space filling curve, parallel collision queries. Again, each of them is a sub-problem with lots of papers to do it, but I'll just come out here and we can speed up. So just to show you, we've done lots of this hashing, nearest neighbor, collision, graph search, every step was done on GPU. And when you take an entire system approach, the end-to-end pipeline, it becomes challenging because if any step doesn't become well, MDOS also has to become the bottom. It's like a pipeline process, every module has to work well on GPU and do that well. And when you do the search, so again, if you're interested in that, we have a bunch of papers on that. I don't want to go details about that. But we're starting with these kind of benchmarks. This is a classic benchmark in robot. Of course, these are the exact data right now, not the sensing data. The piano benchmark, the alpha puzzle, these are nasty benchmarks, which community has used for the last 10, 15 years. And we want to see how well can we do on GPU. It's kind of a path we compute, like a piano, how you move a piano from the phone, do it like that. So at least we saw the timing. What you're seeing on the left is the timing on a single core. This is a well-known benchmark. You can potentially take 4 cores and you can parallelize. It's not very hard. You can parallelize. So if you're given a 4-core machine or 8-core machine, you can get 4 to 7 cents speed up, not doable. But for a single query, when we did the entire thing on GPUs, and we did the end-to-end pipeline, I keep on saying this end-to-end pipeline actually was non-trivial. I've done a lot of GPU code, but this is code that my student wrote. It's about 10 to the lines of CUDA code. It's such a messy code that people want a version of that, we don't want to distribute it right now. Because it's a very painful, challenging code, and I didn't write a single piece of it, my student, all the hard work. So, but again, we're able to get about 100x. So what used to take of the order of 2 tenths of seconds, we're bringing to milliseconds. And it really parallelizes very well, something like this. And the thing was, ultimately, the planner performance depends on whether you can pick smart samples. You can't guarantee how long the planner will take. It depends on the narrow passages and how many samples you do. And again, what we want to show with a log plot, it really scales the number of samples. I can't tell you how many samples you would take, but at least I can tell you it parallelization scales the number of cores. And then within the whole LSH-based, it's called locality-sensitive hashing, we use a very key sub-problem. Again, we should scale. Every step is parallelizable and scalable. Showing every step is scalability was very important for us to deal with that. And this is, again, GPUs can be done for a whole variety of search problems. We can talk about this later on. Search is a big business. We'll do it. We'll do this. Let me go to the last part of the talk, just to show you this thing. So all this was first part dealing with noisy cloud data for a single robot, real-time planning. But a lot of what people are doing right now, for a lot of complex platforms, multiple robots, they think a robot is still too dumb. So there's a big school of biological thought that we don't think they can build a robot as smart as human, maybe not in our lifetime. Then we take lots of simple robots and do them together to do complex tasks. This is swarm-like thinking. How honeybees make a honey nest. How birds fly. There's a lot of biological features that way. So this has been a hot topic in robotics for the last 10, 15 years. How do you planning and for these kind of robots and with sensor error? So this is what we've been working on. Can we do some kind of smoothness and navigation of multiple robots, especially taking into account, we know how to do it for exact planning, with the exact description. But again, remember we're dealing with a very uncertain world, with noisy data, because that's what it is. So right now, for the work that we've done, we're focused mostly on what we call differential-drive robots. This is one class of robot, but actually, believe it or not, it's a very powerful class of robot. All your Roombas, iRobots are differential-drive robots. So robots are cheap. I don't know how many people vacuum cleaning, but I could put 10 of them. They're cheap. All your wheelchair robots are like that. So we looked at this. There's some dynamics problem with differential-drive robots we exploit them quite well right here. Now there's been lots of work on on robot motion planning and the different kind of approaches. But what we were looking was a couple of things. So first we looked into a lot of characterization of these specific robots. There are multiple shaped differential drive robots. This is exact mechanical characteristic differential drive. If you have the background, it's trivial. If you haven't seen it, I guess I shouldn't really go into details of that, but just to let you know. But they have a model how you model the noise. And the main mathematical abstraction is you get differential drive kinematics. You basically got the front and the two individually actuated wheels, and you have basically the center point, the P, which is described by two wheels, and how the motor actuator works, how the robot moves. It's a basic mechanism we use, and you basically in this case take into account the dynamics of the mechanism and take that with planning into account. You take the differential constraints, you can model them with this first order partial differential equation, and again, you got the bounds on the curvature of the part. Your Roomba or this kind of robot, wheelchair, you can't make the sharp right hand. You got bounded radial curvature. That's a field dynamic constraint you got to take into account. You model them for a bit like this, and you do this right. Now the big approach that we've been pursuing, and it's kind of hot in robotics now, for multi-robot coordination, there's a concept of velocity obstacles. That for every robot, this was designed for by Fironi and Schiller, a very nice paper about 12 years ago. For every robot, you come with a range of velocities. It was designed for a single robot in dynamic environment, like a car like C. You take in the dynamic obstacle, and you come with a region of velocity robot can take without collide. So they did this work about 10 years ago, was done. The work that we have done at UNC, one of my postdocs, when they work in the very idea concept called the reciprocal velocity obstacle. We given two robots shown A and B, which were different circular shape. We did the Minkowski sum. And for each robot, you're figuring out what's called RBO A versus B. It gives you a set of velocities that RBO can take, which you not avoid collision with B. But the big thing that we have a velocity obstacle is we can give smoothness guarantees. So previous work never gets smoothness guarantees, and we do it. Let me just show you how it happens. So every scale it happens. Think of two humans or two robots, like blue and green. I'll play this again. And they have to walk. But the previous velocity obstacle, you kind of look at each other, and you kind of react. You get this noisy motion, but actual human motion doesn't have that. It's oscillation. So we give the concept RBO, we guarantee you smooth motion like this. So not only we give you guarantee to give safe navigation, but we also give you smooth navigation. So this is something we did. This is stuff you saw in the game video. How we use RBO, because there were virtual characters, there was no noise, you get smooth motion, it works out. Now for real robots, when you come across, there are two problems. One is we take into account dynamics. So we have a concept called acceleration velocity obstacle, which is like an ICRA in about 2 weeks, or 1.5 weeks. We take into account acceleration constraints. And again, I don't want to bore you with the math right there, but you can come with the notion of acceleration velocity obstacle. It's certainly much more complex, the degree 4 curve we get. Now, especially but for the differential drive robot, the math becomes quite manageable. We exploit that formulation quite effectively. And ultimately, what we're doing here is that for each of these robots, we come with optimality constraint. We can prove this to you that you get a smooth path, which can take into account dynamic constraint and some sensing of noise, and basically making sure that the path is good. So just to show you how this works, I'm very close to time. We set up a simple setup. We are cheap. We don't have expensive robots. We bought a bunch of these iRobot robots, $450 each. And to do the tracking, we put up a simple camera at the top. There's a camera track, and every robot you can see has a separate landmark, which, with a simple vision-based tracking, this landmark will do it, and they have Bluetooth control. And we just did an exercise, let these Roombas navigate. But they go to avoid collision with each other. They're coming very close. Most of the time you see work on multiple robots, what most people do is they divide the space. Like you do that part, you do that part, you do this part. They physically divide and never come close. You don't see too much work in robotics. It's like almost like humans. We pass through each other, almost just touching or not colliding. We just do it. We want to do a similar thing for robots, except you got dynamic constraints, you got noise. We do that, and this setup we did. This is like the path that shows up, the path that, and we give you smoothness guarantee, the path that actually C1 continues to. This is where it comes up. So this is experimental results for showing the path, how different robots come together. And let me show you a video. So again, this is a real-time capture. So there's a one camera, it's actually distributed, they're tracking it, but these robots are going through this thing, they're passing smooth and they just barely touch each other. So this is purely automatic navigation. Of course, you can see robots were wandering aimlessly, we didn't really set up an intelligent task. but they all track with the camera's noise. I'm sorry about the video quality right there. That's not a problem. This is a video codec here. But you get all the robots together, and you see they all, even there's a noisy data you're getting because they don't have exact tracking. There's a camera noise, the Bluetooth sensor noise, but even the presence of noise, we can show these robots still navigate smooth. So this is the stuff we can show right now, a very good smooth navigation procedure. Of course, we take into account differential-drive robot because the math is manageable. If you give me some very challenging robot, I'm not sure I can give you the guarantee the smoothness because the dynamic constraints will be too high. But this is where a lot of cool research can be done and make things come up. I think I'm getting close to 11 o'clock, I should start to wrap up. So this case we have shown you for the first algorithm within a smooth and collision-free motion for multiple differential robots, and at least in our lab setup, we can show quite effective thing. One of the things we're doing right now, and I'm sure a lot of people at this campus are doing, the quad rotors. It's a very fine, cool thing. And this is like one new thing happening in planning. At least when we come to the planning, from a computer science perspective, a lot of cool stuff is happening in planning and control. How do you steering, which is still smooth and not deal with that? We got some results in our simulator, but we haven't taken into a real account this thing. It'd be good to see multiple quad-rotor flying. You see these cool demos on YouTube. There's a group at Vijay Kumar at UPenn, a group in Switzerland doing it. But typically they show one or two quad-rotor which are physically isolated. I would love to see, imagine multiple of them flying like this, just like you saw robots, going like that. And I think we're pretty close to, because the dynamics and the control of quad-rotors can be exploited. There's some new work which can do that. But hopefully I can show you the next time here. So just let me conclude, I started with giving you the overview of motion planning. A problem came out of robotics, but was great, but everything but robotics. Success outside robotics. So to bring it back to the robotics community, we had to come with the oxymoron term, physical robot. In fact, I'm doing a workshop, an ICRA, more physical robot. Somebody said, what? Any robot is not physical? I'm sorry, but that's what blame all the motion planning people, they diverted, they went in a different wrong direction, they come back with the right problem. Big technological success, but there's a lot of more interest, and especially this is happening now because you see robots. See, 20 years ago, there was not such robot like PR2. There was so much sensing computing. So now you have a mobile vendor like PR2. Yes, it's got a lot of money today, but the price will come down. You got 8 cores, you got all these fancy sensors. In fact, they do this exercise like go and grab a beer, get me a cup of coffee. People are hoping that even Bill Gates saying, the next big thing is personal robots, especially there's a lot of attention in countries like Japan, with an aging population. You need a human assistant personal robot, help people dress up and all that stuff. There's a lot of stuff happening out there. For those special tasks, you're still dealing with uncertainty, you still need real-time processing, and we can do that there. So this is basically I've shown some preliminary work on dealing with point cloud data, real-time planning, and other thing. And in a few cases, we've done the work with PR2 people in Willow Garage, and also the work with Roombas there. And of course, just want to thank everybody here, and I'll be glad to take any questions anybody has.
Sure. All right. Questions?
What was GPRL in your blocks?
There are two kind of planners. So one is called the PRM, actually the global planner with a full roadmap, and CPRM is one of them, the lazy version. So you suppose sometimes you build a PRM. Once you build a PRM, then you can any number of queries. But when you do dynamic scene and real-time scene, I don't want to build a global structure. I build a lazy version. It's about single queries. So if the dynamic environment is changing, like you're doing real-time planning, why should I build a global structure if it won't last? So there's a single query lazy planner and a global planner. So single query was much cheaper.
Other questions?
Have you considered collisions among objects whose shape changes during their movement?
Yeah, so that shouldn't be a problem with this. It's called deformable objects. In fact, remember one of the demo I showed you was that catheter insertion of a deformable robot. In that case, the robot was going through non-rigid simulation like that. But that would be a problem because in this case, we're anyway assuming that you're getting point cloud on the fly through laser rate finder. So if the object shape changes, I don't worry about that. I just start from scratch. So that really doesn't bother us.
In my lab, we're also doing a similar project with collision avoidance with iRobot. And did you ever put, a stationary obstacle in with the iRobots? Because how are you seeing the difference between another robot or an obstacle?
Yeah, so that's not very hard, because actually the original velocity obstacle was designed for a single robot with moving obstacle. See, what's the difference between a robot and obstacles? By definition, is an obstacle is done, whether stationary or moving, is following a predefined path. A robot is a smart one, like humans. I react to you, you react to me. For obstacle, you're going to follow your path. I don't care what's in the obstacle. So the example we were showing was multiple robots together, multiple smart people. So, but the obstacle, BO formulation works for obstacles actually much easier.
Because ours, we're actually building a map, so we're trying to see the difference between, a dynamic object and a stationary object. Are you marking them? I know your cameras can tell which one is a robot.
In this setup, we just make everybody, we put, just identify robot, put simple landmarks on that. But I'm just saying, even the obstacles, basic obstacle basically either they're static or they're following a predefined path. I think that is, to me, an easier problem than dealing with multiple robots. Because the point in the robot was, like, if you will say, suppose you're there and I'm there, right? You move right, we somehow, actually, humans do it, make an eye contact, and we're like, okay, I'll go like this, you go like this. We have this implicit communication. But if you don't have eye contact, this thing, I sense you, sense me, I move left, you move right, there will be a oscillation leading to it. So with obstacles, because obstacles are going to follow this path, you already know the path. So you can easily figure out your way sitting around. So to me, that's a little bit of easy piece. Yes, sir.
What about a situation where you have one robot that wants to get from A to B, and another robot that wants to keep it from getting to B?
So these are good guys and bad guys, right? So right now we're assuming that everybody is cooperative, and we share the load. Like in this case, our hope is that we're doing all the good work very easily with this thing. What happens if one of you is a bad guy? This is called pursuit. There are a lot of problems with robotics called this kind of blocker problem, pursuit evasion problem. So we can play these games. You can always I don't want to get you out of the bedroom, right? I block you, right? What will you do, right? So right now we haven't tried that out, but in this setup we're assuming that they all are good cooperative robots. They all want to do their goal, and they all share the load, and being good citizens, and they all get out smooth and navigate easy.
The randomness in estimation of the obstacle's velocity, is that directly can be incorporated in velocity and acceleration obstacles?
Yeah. So in this case, actually, see, every robot is working as a distributed robotic. Every robot basically is computing its own acceleration velocity obstacle. So what it needs to know, who are the people next to me, what is their velocity, and what's their position. And based on that, like if I know he's A and I'm B, I'm doing my RBO B superscript A or ABO B superscript A. I know where he's heading, I'm heading, so we all compute in a distributed manner ABO. And so we only need to know for the nearby test. But of course, the point is that I don't have exact velocity, exact position. The data that I get from camera is noisy. So that's where we did this kind of acceleration velocity of it with noisy, which still give you smooth motion, but doing dynamics. So we assume what you're getting is a noisy estimation of both position and velocity. But you only need that for nearby obstacle. When I'm walking, I only care about the people next to me. I don't care about the people which are 30 meters away. And the same concept locally, you do that and you compute ABO by taking into account other robots which are very close proximity. But it takes into account the noise.
Just one. So this communication is based on the nearest neighbor topology?
No, the setup is totally distributed.
So there's no communication?
There's no centralized computation. We just assume that you have some sensing that will let you know that who are the robots nearest to you or what is their position and velocity. In this case, we simulated that by having a centralized camera. But all we need to do is the computation rate is every robot, every autonomous agent is computing its own RBO or ABO. Reciprocal velocity obstacle. But you need to know the velocity and the position of nearby robots with some noise. So how you can get that, like we humans use our eyes, that's what we do. You could have some simple rain sonar sensor, you could do that. But the whole planning is done in a very decentralized, distributed manner. But we assume you figure this out, that's how you figure this out.
Other questions?
But that's what to do with cars, that's what Google is doing. You're putting all laser and lidars there. It gets a pretty good scan on nearby things around to you, and you can, based on time of return, you can figure out those. It's not very hard to figure.
Something like cooperative algorithms, they sometimes assume some sort of application.
Yeah, so there's a notion called centralized and decentralized. So we are looking at decentralized scheme because I'm also doing this thing similar to cloud with 10,000 agents. So centralized scheme will not scale to that level. Now for something like the question he asked, will my decentralized scheme work well? I don't know. But at least our framework is very decentralized because ultimately we're doing crowd simulation, we're doing robots, and we are going for large numbers.
Right, so what I'm going to suggest is that, I know that some of you have constraints, so if you want to talk to Dinesh, you can come to the podium and talk to him. Otherwise,